Hello everyone. In this video, I'm going to talk about constant acceleration. Okay. Oh, sorry, constant acceleration, and it's almost the end of the 1D kinematics. And why do we have to talk about constant acceleration? Because in a further chapter or further section, we are going to do some calculation on free falling motions and projectile motion. And these two motion, we can simply regard them as a constant acceleration motion. And then so that's why we need to introduce the constant acceleration. And this projectile motion and free falling motion is pretty, yeah, you will see in everyday life. So this also very very useful calculation. Okay. Okay, so and let me first see. Okay, so that's how we start. So it's constant acceleration, right? So constant acceleration, can you accept this idea like because since it's constant acceleration, so it's an instantaneous instantaneous acceleration is equal to average acceleration. Average acceleration. Can you imagine this? Because it's constant acceleration. So instantaneous acceleration is equal to average acceleration because average is constant. But sorry, the acceleration is constant. So no matter it's instantaneous value or average value, the acceleration always constant. Okay, so if you accept this concept, we can keep continuing. Okay, so let's write down the definition of average acceleration. It's minus velocity minus initial velocity divided by time interval. And for the time interval, because we can always say the origin of time, so we always say the initial time is 0. So we can always write down this because we can always choose the time origin. Okay, so the initial point is 0, and it's equal to instantaneous acceleration. Okay, so and then we arrange this equation, we will finally get the final velocity is equal to initial velocity plus acceleration times time duration. This is the first equation we will have. And okay, in this section, we are going to reach one of the important and useful tool called equation of motion. Okay, we will finally reach this called equation of motion. Okay, equation of motion, it will give you the trajectory functions. Okay, and we will get there. Okay. So and next thing I want to say is I want to show. Let me see the cheat sheet. Okay, the next thing is the average velocity. Average velocity. Okay, let's write the average velocity. Average velocity, remember, final position minus initial position, and divided by we use the same setup t minus 0. Okay. Okay, so then we will get the equation like this: final position equal to initial position plus average velocity times t. Okay, so the final equation of motion show finally what we will get equation of motion is a relationship between the position, velocity, and acceleration. Okay, so right now for this xf and for this one, the final position is equal to initial position plus velocity times t. We only have information for position and velocity. There is no information for acceleration. So we want to do a little more further tricks. What's the tricks? And what's the tricks? The trick is this. We want to replace the average velocity. Okay, average velocity. Okay, and how do we replace the average velocity? Because the average velocity is equal to the displacement displacement divided by time interval. So right now, how do we replace this average velocity? We have nothing else to replace. We have nothing to replace this term. So we will make a trick. The trick is from this one. Okay, the trick is from this one. Uh, so you look at the final velocity is equal to initial velocity plus acceleration times t. So anything because the acceleration is a constant, so actually you can see this is a straight line. This is a straight line. Yeah, it's TRAIGHT. If I draw this in picture, what it will look like? What it looks like? What it looks like? Okay, let me draw down the picture. Wait for me for a moment. Let's draw a VT diagram. VT diagram. So if I draw is like this equation. If I draw a picture, it looks like this. So if this here is T0 VI and here is VF. Okay. Okay, so if I draw this equation, it looks like this. So it's the velocity is keep the velocity. If the a is positive, the velocity is keep increasing from vi to vf, and the slope, the VT diagram, the slope is a. Okay, this is a graphical representation of this equation. So what's the trick we are going to make? Okay, so that's the trick we're going to make. Okay, we use the concept we mentioned before, not concept, the definition. Last time, what's the definition of instantaneous velocity? Instantaneous velocity is dx over dt, right? If I rearrange this, so dx is equal to velocity times dt. Okay, let's look back into this diagram. dt means very short period of time. So if I say this code dt, this code dt, this code dt, and here, if dt is very small, but because I have to draw on the screen, so so you have to exaggerate. Actually, dt is very small. Okay, if your dt is very small and this value we call it v. Okay, so this value is called v, but be careful. Like I said, dt is very small. So actually you can just the value on this straight line at this point. Okay, so what's the, so when v times delta t, v times delta t means this area. Okay, this area is delta x. It's a small displacement. Okay, so if I slice this diagram, continue slice the diagram. For example, I keep to do a slide here, or do a slide here. Sorry, do a slide here. Okay, and that's a bunch of them, bunch of this slide. In under this area, I do a bunch of slide, and very small. Every slide is very the width is very tiny, delta t. So if and then I summation all of them. This will become a total. This will become a total displacement. Okay. Total displacement. Total TOTAL. Total displacement. Displacement. Oh, okay. So okay, if I do the slide on lots of slide on this diagram, we add all of them. It's the total displacement. It's a total displacement. So We can reach right now a temporary conclusion is that let me draw this again. VF. So the area of VT diagram, the area of VT diagram is displacement. Oh, this is displacement. Okay, the area of VT diagram is a displacement. Okay, so what's this going to do with the substitution of the average velocity? Okay, we can use this diagram to make a substitution on the average velocity. How? So do you know how to calculate area under this curve? Okay, under this curve, do you know how do you guys remember how to calculate area under this curve? I think high school teach something about this, how to calculate the area under this curve. I forgot the English name. Let me check this. B. Oh, sorry. Yeah, what's the English name? 梯形，中文 called 梯形 but what's the English? I really forgot. 梯形。Okay, trapezoid, trapezoid. Okay, trapezoid. The area of a trapezoid. Okay, the area of a trapezoid and the formula is here. Okay, do you know how to calculate area of a trapezoid on this area? Do you remember that? Okay, I hope you can remember that. Okay, so the area, let's calculate area under this. The area is VI plus VF times T over 2. Okay, so the area, the displacement is like this: VI plus VF times T divided by 2. So this is a displacement under this the area of this the area of this area of this area. This is the area. Okay, so could I replace this if I can find something called I have average velocity, but in the same time I have the same displacement. Can I find this V average? The average velocity times the same time has the same displacement as displacement of this displacement under the same situation, the constant acceleration situation. So I think we can, because after this equation you divide it by, and you can kill this. Okay, and then you will lead the V average VG equal to VF plus VI, initial velocity plus final velocity divided by 2. But be careful, this conclusion only for constant acceleration. This average velocity, the initial velocity plus final velocity divided by 2, it's only valid for constant acceleration. If it's not constant acceleration, this relationship doesn't hold anymore. Okay, so we use spend some time to explain this. Okay, so we finally can use this trick. I replace the average velocity by the initial velocity, the average of initial velocity and final velocity. So what we are going to get? Okay, let's keep writing. So we will get xf equals to initial operation plus vf plus vi times t. So you will say I replace I replace V average by this, but we still don't have any information about the acceleration. So what we are going to do? Can you figure it out? I, we are really close. We are really close. Now you have two. You have if you want to get the equation of motion. Let me see. You want to get the equation of motion. Let's see. Okay, if you want to get the equation of motion. Okay. Oh, let me rewrite this. Make it more readable. Okay. So if one get a equation of motion, okay, let's replace VF. VF equal to VI plus A times T. So if you do this replacement, what we are going to get? What we are going to get? Xi plus 1 over 2 VF VI plus AT plus VI times T. So you will reach a famous conclusion: Xi plus VI times T VIT plus 1 over 2 AT square. So this is a very famous result. This is I call equation of motion. Equation of motion. And this equation is very beautiful. Why it's beautiful? Because the final position, if you want to get the information of final position, you only need the information at the initial position and initial velocity, and of course initial acceleration, but acceleration constant. Okay. If you have information of initial position, initial velocity, and initial acceleration, and then you will get the information of final position. So all you need is the initial point information. You need only initial point information, and you get the final point information. So that's the feature of classical mechanics. I call it determinism. That's the feature of classical mechanics, determinism. Your final point is all related to your initial point. Yeah, nothing else. Your initial point is right. Your final point, final point is right. Okay, so that's very crude, right? Yeah, it's all determinism. Okay, so classical mechanics is determinism. From the kinematics, you can feel that it's determinism. Okay, so maybe you heard about the quantum mechanics. Quantum mechanics is not determinism; it's kind of randomness. But we won't talk about quantum mechanics in this course. Just let you know the difference. So this equation of motion we will get is very useful. And there is another useful equation we will obtain from by this. So let me think it is small enough, or is small, so I roll it up a little bit. So there is another equation we can obtain. What is it? Let me write this again. Xf equal press I. Let's start from here. Vf plus Vi times T. And this time I replace T. Okay. Replace this T. So from where? From here. Let me take from here. T is equal to A VF minus VI, right? Yeah, from here. Okay, from here I can replace T by VF minus VI divided by acceleration. And after this substitution, I think you will get this. You will get, let me write it slowly. You will get X equal to Xi plus 1 over 2 VF plus VI. is AVF minus VI, and then we will reach also another famous equation. This some you need to do some algebra. VF squared is equal to VI squared plus 2A XF minus XI. Okay, XFI sometimes people you will see write delta X, but it doesn't matter. If you understand delta X is equal to XF minus XI, it's fine. So we will reach another useful equation for 1D kinematics. This one, VF squared equal to VI squared plus 2A delta X. Okay. And the other useful equation is this one, equation of motion. That's the XF. Okay, this one. The final position equal to initial position plus V times T plus 1/2 times A times T squared. Okay, these are two useful equations for 1D kinematics. And I think for next video, I will show you some example for use these two equations to solve the 1D kinematics problem. Yeah, this video really takes a lot of time and explanation. Okay, so I think the most difficult part you see is is you need to understand why V average is equal to the average of initial velocity and final velocity. Okay, for constant acceleration. I have to say that's for constant acceleration. And how to prove this is use the area under VT. Area under VT diagram. Area under VT diagram is displacement. Okay, can I find an average velocity times the same time interval with the same displacement? Yeah, this is a very simple proof, and you will get this. And then do the further things, do the following derivation, you will get the equation of motion. Okay, so that's pretty much about this video. I think it's a little bit too long, so I'll stop here and see you for next video. Bye bye. It's kind of real long. I should write this. 20 minutes.